Hello, I'm Dr. Chanak Vijayaratna, the CEO of the Sri Lanka Olympiad Mathematics Foundation. Now I'm going to discuss SLMC 8 2020/21 hard questions. So this is the third part of the video series. In the first two videos, I discussed easy questions and medium questions. Now we have to discuss hard questions. So as I mentioned in my second video, even in the International Mathematical Olympiad, the questions that the contestants get on the first day, 3 questions, on the second day, 3 questions, and on the first day, 1, 2, 3, 1 is easy, 2 is medium, 3 is hard. And on the second day, they get 4, 5, 6, 4 is easy, 5 is medium, and 6 is hard. So in the Sri Lankan mathematics competitions also, the first 10 easy, second 10 medium, and the third 10 hard. Right now for the hard questions, right, you get 8 points for the correct response, 3 points for the no response, and 0 points for the incorrect response. So you have to select your response very carefully, right? Because if it is incorrect, you get 0, and if you leave it, you get how many points? You get 3 points. Okay. So let's start looking at the hard questions. So number 20. So we have a question about the politicians in the land of liars. Now they lie on weekdays, and they don't lie on weekends, so they tell the truth, right? So when they're at home, they don't tell lies, but they are with the public on weekdays, they lie, right? Okay, so the question is, on what days can a politician in the land of liars say, I will lie tomorrow, right? So since actually this is regarding a statement that is made on a day, and then it is something about what he will do on the following day, right? So therefore, we have to look at different consecutive 2 days, right, to answer this question, right? So this means that we have cases, right? So case 1, we could have 2 days, right? And on the first day, he lies, and on the second day also he lies, right? And then so the case 2 is on the first day he tells the truth, and on the second day also he tells the truth, right? And case 3, on the first day he tells the truth, and on the second day he lies, right? And on the first day he lies, and on the second day he tells the truth, right? So if the politician says that I will lie tomorrow, on a day he lies, right? That means this case, right? Then to lie tomorrow has to be, so he said this on a day he lies, right? So that's a lie. That means he has to tell the truth on the following day, right? But the following day also he lies, right? So therefore, this case is not possible, right? He can't make the statement he or she on a day he lies, and the day is followed by another day of lying, right? He can't do that, right? So what about, he tells this statement on a day he tells the truth, and the following day is also he has to tell the truth. So if he says I will lie tomorrow, so that's a truth, right? Then he has to do it the following day, he has to lie, but the following day he has to tell the truth, So then he can't do that, right? So this case is also not possible, right? Now, what if he tells this statement on a day he has to tell the truth? I'll be like tomorrow, right? And then tomorrow happens to be a day he lies. So that's fine, right? He says this, he or she says this on a day he has to tell the truth. So I will lie tomorrow. Then it has to be true, and the following day he has to lie. So then this is possible. And so what kind of days you have for this case? So then a day telling the truth followed by a day telling lies. So that has to be Sunday followed by Monday. And then he tells this on a day he lies, and then he actually lied. That means he's going to tell the truth next day. And next day happens to be a day he has to tell the truth. So this is also possible. And what are the possible dates? So it has to be Friday followed by Saturday, right? So therefore, the answer is only Sunday and Friday, right? So that's a very interesting question, right? So let's move on to the next one, number 21. So let me erase all this. Right. So number 21. So Meena has this misconception that if she has a fraction with the numerator with 2 digits and the denominator 2 digits like this, right? So there's a digit common to numerator and a denominator, and she can cancel this digit, right? And gets the correct answer, right? So this is 408, and this is 102. And this happens to be correct, right? But we all know that this is not a correct procedure, right? Now, how many 2-digit numbers are there, right? So A, B, so let's put a bar on this, and BC, right? And then you can actually cancel this digit B, which is common to the numerator and the denominator, and you get A of C, and this is half, correct simplification, right? Okay, so now what we have is that 10A plus B, right, over 10B plus C is equal to A over C is equal to half, right? Now, here we have actually so 2 equations, right? One is that 10A plus B over 10B plus C is equal to half, right? Other one is that A over C is equal to half, right? So this gives us A is, okay, okay, CA is equal to 2A by cross multiplying, right? And what do we get from this one? So by cross multiplying, we get 20A plus B, 2B is equal to 10B plus C, right? So we can substitute for C. So this is 10B plus 2A. And if you simplify, you get 20A minus, I bring 2A to this side, right? 2A to this side, to the left. And I get 18A. And then I bring 2B to the right-hand side. So 10B minus 2B is 8B. So let's divide by 2. So A is equal to, sorry, 9A is equal to 4B, right? So this tells us that, right, so 9 divides the left hand side and the right hand side, but 9 does not have common factors with 4 except 1. So this means that 9 divides B, right? So actually here I'm using a little result, right? Called Euclid's lemma. A very intuitive result, right? If A divides BC, right, then, okay, and A and B don't have common factors other than 1, right? So that means the GCD of A and B is 1, right? So then A divides C. So that's what I used, what I used here, right? So 9 divides B, that means B could be only 9, right? So then what is A? So A is, right, from this, so 9A is equal to 4 times B, 4 times 9. So this means that A is equal to 4. And what is a C? So C is equal to 8. So actually we get the number that, the 2-digit number we have here, right? 49 over 98. So the answer is, right, just 1, right? Okay, so hope you followed it, right? If not, please go the video again, and then you can actually understand this by revisiting, right? So this is a good strategy, right? Maybe you will not understand something then and there, right? But if you think about them later, or if you revisit the video, you can understand, right? Okay, let's go to the next question, number 22. So let's erase all this, okay, and get this lasso tool. Right, so some left over, let's cut them. Right. Okay, number 22. We need to find the sum of all positive factors of 2020. So let's factor this. We can divide this by 4. So 4 times 505. So the prime factorization of this is 2 to the 2 times 5 times 101, right? And if you take any factor of this, right, any factor of 2020, it is of the form 2 to the A, 5 to the B, so A and B exponents or indices, powers, right? 101 to the C, right? Now here, A can take values 0, 1, 2, right? And B can take values 0, 1, right? And C can take values 0, 1, right? And then how many factors are there? So the possibilities for A times, sorry. So the possibilities for A times the possibilities for 2B times possibilities for C 2, right? So we have 12 different positive factors, right? So we can write all these 12 and at the mark, but there is a long method, right? Maybe there's a shortcut method here, right? Now, what if, we write, these powers of the prime factors, right? Here, we have 2, right? And 2 can occur in a factor, right? Maybe there's no 2, and maybe there's 1, 2, and maybe there are 2 2s, right? So let's write it as 2 to the 2, right? 2 to the 2, right? And then we could have, no 5s, and then 1 5, right? And we could have no 101s and 101, right? Now, can you see that when you expand this, right, you get all these 12 positive factors. Now, one thing is that, again, right, so this has 3 terms, this has 2 terms, and these 2 terms, right? So we do get 12 terms when you expand this. Now, are those 12 terms exactly the positive factors of 12? Let's see. So we get, the positive factor 1, right, when you multiply these 3, right? And then you get 5 if you multiply this and this, right? And you get 10, right, if you multiply this, sorry, 101, right? This and this. So likewise, you can see that all these terms are exactly the positive factors of 12, right? So now actually we can simply find this product. So this is 1 plus 2 plus 4, which is 7 times 6 times 102, right? And this is 42 times 102. And let's calculate that. So 102 times 42. So 2 times 2 is 4, 0, 2. 4 times 2 is 8, 0, 4, right? Right. And then when you add them up, 4, 8, 2, 4. So the sum of these positive factors is 4,284, right? So do we have that in our answers? Yes, of course, right? So this is the answer, right? Now, let's go to number 23, right? Number 23, and let's get rid of all this. Right. So number 23, Vijayaratna has 5 red marbles, 7 green marbles, and 9 blue marbles in a box, and then he's going to pick 3 balls, right? 3 marbles from this box without looking at the marbles, right? And then you have to figure out the least number he has to take 3 marbles of the same color, right? If Vijayaratna is lucky, right? So when he picks up 3 marbles, they'll be of all same color, right? Now, what if that this is Vijayaratna's unluckiest day, right? On his unluckiest day, right? How many he should pick the least number so that he is sure, 100% sure that he has 3 marbles of the same color, right? Of course, then he can pick all these marbles, right? 5 plus 7 plus 9, right? 12 plus 9 is 21. So if we pick all 21, of course, then he has 3 marbles, right? No, the least number on his unluckiest day, to make sure that he doesn't have to depend on the luck and he has 3 marbles of the same color, right? Now, let's look at, so he picks up the first marble, so it happens to be R, right? Next one, R. Now remember, this is his unluckiest day, and for the next one, he doesn't get R, he gets a blue one, right? Now next is also blue, right? Since this is unluckiest day, next one he gets not a blue or red, he gets green, and the next one is also green, right? Now it doesn't matter, whether it's unluckiest day, right? Because the next one has to be, right, either R or B blue or G green, right? So in either case, if he gets an R, he has 3 marbles of red color. If he gets a blue, he has 3 marbles of the blue color, and if he gets green, he has 3 marbles of the green color, right? So that means on his unluckiest day, if he picks 7 marbles, right, then he has 3 marbles of the same color. Okay, so we worked out the worst case scenario, right? The unluckiest day scenario, right? Okay, so the answer is 7 marbles, right? Okay, so let's go to the next question, number 24. So let's move this up, right? Number 24. How many 4-digit numbers have the property that the product of their digits is 21? So 21, right? Its prime factorization is 3 times 7, right? So then, since this number has 4 digits, right? The digits of the number, right, have to be, right, 1, 1, and 3, and 7, right? There's no other way. So, how many 4-digit numbers you can make from these 4 digits, different numbers? So we could actually have that rectangle, right, divided into 4 boxes, right, like this, right? So in how many ways we can place 3 and 7 in these boxes, right? So let's say that, we put 3 first, right? And you can do that in 4 ways because there are 4 boxes, right? Now, 1 box is gone and we have 3 more boxes, 7. So it is 4 times 3, 12, right? Now here, we don't need to divide by 2, like, in some of the problems we discussed earlier, because now the order matters, right? 3, 7 and 7, 3 are different, right? So we have 12 ways of placing 3 and 7, and then in the remaining boxes we can place 1, right? So the answer is 12 ways, right? We have the answer 12 years, right? Right. So that was short, even though this is a hard question, right? It is like that. So once, if you know how to do it, then if you can find the idea quickly, you can do it quickly, right? So let's go to number 25. Right. How many 4-digit numbers consisting of non-zero digits have the property that the sum of their digits is 7, right? Now, there's an experiment coming, so let's wait till it passes. Okay, so the sum is 7, some of the digits, right? Then you can see quickly that if all the digits are 2, right? So 2 plus 2 plus 2 plus 2 is 8, right? And the smallest number we can get without the 1 is 8, but the sum of the digits is 7. So that means there have to be digit 1. so we have cases, right? Subproblems, right? So we have 1, 1, right? So 7, right? So let's say that, okay, 1, 1 and 3 2s, right? So how many different 4-digit numbers you can make? Well, this digit 1 can be the first one, the leftmost one, and the next one, right, coming from left. So we have 4 numbers, right? 4 numbers, right? And case 2, we could have 2 1s, right? And then 2 and a 3, right? Now we know that we can place these 2 and 3, right, with order with order considered, right, in how many ways? In the early problem, we found that there are 12 ways, right? So in 12 ways, we can place 2 and 3. Order is taken into consideration, 12, right? And then the remaining boxes, remaining digits can be 1, right? So that means we have 12 numbers, right? Right, case 3. So we could have 3 1s, right? And a 4. So this again, case 1, right? We have 4 numbers. So how many altogether? So we have 4 here, 12 here, 4 here. So it is actually 20, right? 16, 20. So do we have the answer 20? Yes. Right. Okay, now let's go to number 26. So let's erase this. Right. Now, here this question tells us that the ancient Egyptians used a base 10 non-positional number system, right, with these numerals, right? Actually, yeah, these are pictures, right? So it is a base 10 non-positional system, right? Now, we have a base 10 functional system, right, with Hindu-Arabic numerals, right? So, so since, it is non-functional, right, they had to use lots of symbols to denote, to write their numbers, because they can't use the same symbol, right, with different values. For example, now in our system, right, if you take the digit 1, right, so it could be just 1, in the unit space, right, and it could be, so if you take the number 1111, right, this actual number is just 1, and this one is for the 10, and this one is for the 100, and this one is for the 1000, right? But the ancient Egyptians system was non-positional, right? So therefore they had to use different numerals, right? So we are told that this represent this number, right? So you can see that there are 4 frogs here, right? So the frog, the tadpole, 100,000, right? So this means that we have, 400,000, right? And then we have 5 fingers, right? 5 is actually 10,000, right? So it is 50,000. So 50,000, right? So it should be right. And then these lotus flowers, and there are 9 of them, and each lotus flower is 100 times, so 1,000 times 9 is 9,000, right? And then 6 coil ropes, each coil rope is 100, so it is 600. And then 2 heel bones, and that is 20, and 3 strokes, and that is 3, right? So then we have this number 459,623, right? Okay, so now we are told that if the symbols represent different non-negative powers of 10 than the ones given in the above table, and the order of the symbols is not important, right? And the same array, this one, represent this number, 945,362, then since we have 9 lotus flowers, right, this has to represent, right, 100,000, right? 100,000. So the answer is 100,000, right? Okay, so let's go to the next question. So let me move this upward, right? Right. So let me erase these. Question number 27. And again, non-negative integer powers of 10 are from 1 to 10,000. So that means 1, 10, 100, and 10,000, right, are represented by these 4 symbols: stroke, heel bone, coil rope, and lotus flower, and tadpole. There are 5, right? So yes, so it is 1, 10, 100, 1,000, and 10,000, right? 1,000 and 10,000, right? Now, this addition is correct. This addition is correct, right? So you can see that on the left, you have a lotus flower, right? And actually you have 9 lotus flowers, right? Flowers, hold on. 9 lotus flowers, right? And you have no lotus flowers on the right hand side, right? So here 0 lotus flowers on the right hand side, and we have strokes here, right? Here we have 3 of them, right? And here we have 7 of them. So altogether 10 strokes on the left hand side, and we don't have any on the right hand side, right? And also there is no tadpole, no tadpole, and there's 1 tadpole on the right hand side. Right, now other symbols, right, these coil ropes, right? So we had 1 and 3, and they add up to 4, and you had the 4 of them here, right? And we have heel bones, right? 2 of them here, 5 of them here, and we have 7 of them. right? So this means that the 10 strokes, right? 10 strokes, right? So they represent, stroke represent a certain power of 10, one of these, right? And then since, 10 of these actually disappear, right? Don't, no strokes on the right hand side, right? These 10 strokes must have, become some other power, right? And we have 9 lotus flowers and no lotus flowers, right? Then the logical conclusion is that this lotus flower, right, must be, right, must represent the next power, right? So if, the stroke represent 10 to the A, then this one represent 10 to the A plus 1, right? And then what about the tadpole? Tadpole must represent, right? Let me draw a tadpole here, right? Tadpole must represent the next power of 10, right? So this means that, right, in this sum, right, in this sum, right, in this sum, right, we must have 0, 0, 1 block, right? 0 for the no strokes, this 0 for the no strokes, and this 0 for the no lotus flowers, and this 1 for the tadpole. And then, we have this 4 and 7, right? So that means that we could have 4 here, 7 here, that's one number, right? Or we could have 7 here and 4 here, right? Also, we could have this 100 here, 4, 7, right? And then 100, 7, 4. Sorry, let's use green, 7, 4, right? And also we could have 100, 4, 7, 100, 7, 4. So how many different values can the sum take? It can take 6, right? 6 different values, right? So the answer is, where is it? Here, 6. I hope you like the problem, right? You learned something about the ancient Egyptian number system, right? Their base 10 non-functional system, right? And we get to think in this familiar base 10 system, right? In a different setting, right? We have to think logically to get the answer to number 27, right? Let's go to number 28. And let's erase all this. Right, number 28. Right. So the positive integers from 1 to 300 are written one after the other, and we need to find out how many times 52 occur, right? Now, always, it is easy to break a problem into sub-problems, right? So that's one of the problem-solving strategies, right? Here, what are the cases? So I can see that one case could be this 52 occurs, right? 52 is part of a number, from 1 to 300. So we could have just 52, right? Right? Or we could have 52. We could have 152, right? And we could have 252. right? So this can happen in 3 ways, right? And case 2, 5 may come from 5 from one number, right? And 2 from the number that follows, from the number that follows. Right? So from the first number you get 5. So and that actually must be the last digit, and then the first digit of the next number, right, gives us 2, right? So this way we could have 25 and 26, right? 25, 26. Then we could have, now this is actually the only number from 1 to 99. And what about 100 to 199? Now here we have numbers ending with 5, like 155, but then all the numbers start with the digit 1, right? So then here we have 0 numbers, right? No numbers, because the one follows that, the number that follows starts with the digit 1, so we can't have such numbers. And then what about numbers from 200 to 299? And here the second number always starts with 2, right? So if you look at numbers ending with 5, the last digit is 5, then we are in luck, right? So we have 205 and 206 and 215, 206, 225, 206. So likewise, this goes on till 295, 296, right? So how many altogether? We have started from 0, here, right? 0 here to 9 here. So we have 10 numbers, right? So that's all, right? So altogether we have 3 here, 1 here, and 10 here. So altogether we have 14 numbers, right? So the answer is 14. Okay. So that's a nice problem, right? We had to break the problem into cases, right? And that allows us to count these occurrences, right? That 2 follows 5, right? And we were able to count them correctly, right? So let's go to number 29. So let's move this up. And let's erase this. Okay. Okay, in number 29, we are given the statement, all centipedes have 2020 legs, right? All centipedes have 2020 legs, right? Is false, right? So if it is false, right, in how many ways it can false? Now, if all the centipedes have 2021 legs, yes, it is false, right? So in Roman 1, right, Roman 1 implies that the statement is false, right, correct. And if there's at least one centipede which has 2021 legs, again, the statement is false, right? So this symbol means that it implies, right? We can conclude from whatever on the left-hand side, we can conclude what we write on the right-hand side. And in Roman 3, no centipede has 2020 legs, right? So each one has maybe different number of legs, different from 2020. Whatever it is, you know that again, this statement, Roman 3, implies that the given statement is false, right? But the given statement is false, right? Does it imply that statement 1, or does it imply that statement 2, or does it imply that the statement 3, right? So you can see that, you know, that we don't have that any one of these statements necessarily following the falsity of the given statement, right? It is because now, you know, why, you know, that this doesn't follow from this? Well, actually now we, if you take, you know, Roman 2, right? We could have Roman 2, right? Oh, let's say Roman 3. Okay, Roman 1, right? Let's say that, you know, all centipedes have 2022 legs, right? All have 2022 legs, right? Now, in that case, also the statement is false, right? So let me write it here. All 2000 centipedes have 2022 legs, right? So that also actually make the given statement false, right? But we can't say exactly, right, whether it is all of them having 2021 legs or all of them having 2022 legs. No, we can't say. But we can say that if this statement, right, is false, if it is false, then we can say that there is at least one centipede who doesn't have 2020 legs, right? So there is at least one centipede who doesn't have 2020 legs, right? And you can see that this statement is true, right? In all these cases, right? So in one, all centipedes have 2021 legs. Yeah. So there's at least one centipede who doesn't have. Yes, correct. Right? And even here it is correct. Yes, right? So, but we can say that the given statement, right, false, right? It implies this, right? So the answer is, right, none. So none of the given statement necessarily follows from the falsity of the given statement. So the answer is E, none, right? Okay, so you know, we had to think logically to get the answer, right? Let's look at the next one, the last one, right? So let's get rid of all this work. So let me move this up, right? Now, what is now they up to? Now they has this square, right, with vertices labeled A, B, C, D, right? And there are these lines of symmetries. Right? And then she performs two operations, right, on this. R, rotating the square 90 degrees clockwise, but lying through O perpendicular to the square, right? And then flipping the square along OX, right? So then she does this operation 2020 times, and we need to figure out the position of the square, right, with respect to the lines of symmetries OX and OY, right? Okay, so now if she performs a flip, right, what happens to the square? So the flip is along the OX line, right? Then we have, so AB vertices here and DC here, right? So one flip, right? Now you have to anticipate that in this question, right, we are not supposed to do all these operations 2020 times and figure out the last question, right? There must be a recurring pattern, right? So you are supposed to find the recurring pattern, right? All right, so let's see whether we have recurring pattern, right? And then we perform a rotation, right? So if you rotate this clockwise 90 degrees, right? What happens? So this is about a line through O perpendicular to the square, right? So 90 degrees, right? 90. Actually, it is about the line O, right? So like this, right? 90 degrees, right? Then A comes here, B is here, and C is here, D is here, right? So one rotation, right? And then we perform another flip. So far, we can't find the recurrent pattern, so we had to actually check whether we'll get to the original position, right? So let's see. So one more flip. So along the OX line, right? So then C, B are here, and D, A are here, right? Still, we don't we haven't come to the original position. And one more rotation, right, about O, 90 degrees clockwise, right? So we rotate this 90 degrees about O, right? Now B comes here, A comes here, and D comes here, and C comes here, right? Now you can see that now we came to the original position, right? So that means if you perform a flip, a rotation, a flip, a rotation, you come back to the original position, right? Okay, so a flip, a rotation, a flipped rotation brings us, back to the original position, right? So that means this is a recurring pattern, right? So it has four operations, right? And then, so we have to do all these operations 2020 times, right? And for divide this right? This number, right, divisible by 4. So what do we get? We get 505, right? So then with this cycle, when it repeats 505 times, right, we get altogether 2020 operations, right? And we come back to the original question, right? So the answer is, right, E. We come back to the original question after 2020 operations, right? So is, interesting and easy, right? Because we had to find a recurring pattern, right? And figure out the question after 2020 operations. Hope that you enjoyed these questions, right? So in this three-part video series, I have discussed the question paper um, in completely, right? So please go over the videos, and if you don't understand something, revisit the video and make sure that you understand how each problem is done, right? And hope that you will enjoy this kind of mathematics, Olympiad mathematics, right? And this will sharpen your thinking, your critical thinking, and also you will learn to think out of the box, right? And creatively, right? So I hope to meet you again in a similar video, right? Till then, enjoy doing math. Thank you.